with us. Sir, we extend a warm welcome to you. So before we start, I would like to take few moments to introduce our esteemed speaker. Professor Swarup is a senior faculty member at IIT Madras, working in the area of electrical power systems. His teaching and research span topics such as energy management systems, digital energy, SCADA, protection automation, and control. His ongoing research focuses on smart power grids, cyber physical systems and security, energy management, and digital and numerical protection, all of which are central to modernizing power networks. He has supervised several MS, PhD, MTech, and BTech students and guided research in collaboration with national and international partners. We are delighted to have him with us today. So, with this, I would like to request Sir to kindly take over the session. Thank you, sir.
Okay, thank you very much, Mr. Chaudhary. Good evening, everyone. Am I audible?
Yes, sir. You're audible.
I'll be working. I'm giving this from my residence.
Sir, you may share right now your screen also.
Yeah, I'll share the screen. Is the screen visible?
Sir.
Yes, sir, it is visible right now.
Yeah. I can put it in presentation mode. Now is it visible?
Yes, sir.
Yeah. And please tell me if anything is not there, I can go back to presentation mode.
Sure, sir.
Good evening, everyone. Let me tell you, this is a very interesting topic. So, this is called the smart grid approach to energy sustainability. Sorry, there's a spelling mistake. And resilience. So this is the topic, energy sustainability and resilience. There are many methods, but I'm going to discuss about the smart grid techniques, tools, and approach to energy sustainability and resilience. What is energy sustainability? What is energy resilience? These are the new buzzwords by many people, industries. If you look at the new news which is going around, many universities, India, abroad, and in the industries also use this term as energy sustainability and resilience. Okay? So, as an academician, how do you view this problem? Let us see what is energy resilience. Okay? What is energy sustainability? There are many things around these two terms. Okay? So this is about the speaker. I'm a faculty here. I work in different areas of modeling, operation, protection, SCADA. I'm going to use all of them in my presentation. This is the background of the speaker. I have both academic and industry experience, and I was fortunate to join here in IIT Madras. I work in different areas, power system, knowledge-based systems, and also work with industry like Accenture, Shell, and other things. And this is one of the recent work we have done. So my talk is centered around this. We did a industry work for Accenture and also for Shell. This is what it is. So I just want to tell you that what I preach, I practice. I'm going to talk about what is called energy sustainability is here, and also we have energy management automation. These are the two topics which revolve around energy sustainability and resilience. So this is the contents of the talk. I divide this into three parts. Okay. First, I'll give an introduction to the various keywords like energy transition, why is it required, what is renewable energy integration. You might know all this, but you should also know how this topic plays an important role and what are the solution methods from academic perspective. How do you teach students to this? Okay. Which solution methodologies, which system studies are required for all of it? We know about economic dispatch, load flow studies, stability studies, fault. These are all conventional system studies which we use. But when it comes to the new era of problems like energy integration, energy transition, which studies are required? This is what this present talk is about. And finally, we'll talk about what are smart grids, what are self-healing networks, energy sustainability and resilience, okay, can be enhanced using smart grids, self-healing grids, autonomous grids, futuristic power grids. If you keep following the Power Globe, you can find many PhD opportunities for students in these areas. I've seen many opportunities in these areas which are coming up, okay, and they want students with bright ideas to implement them. So this is what we are going to discuss today. So part one, we'll talk about renewable energy integration and transition. See, all these three topics, energy transition, renewable energy, energy storage, grid modernization, are all integrated, are all linked together. Okay. So whatever we are teaching, okay, we practice. In fact, next week we have an industry which is coming to IIT Madras, which wants to know about grid modernization and energy storage. Okay, that's why whatever I am doing is what is I'm going to present next week as well. Okay. What is energy transition? How do you define? Energy transition is a broad shift in technologies and behaviors that are need to replace one source of energy with another. Which source of energy do you replace? The fossil fuels, okay, which is the source of pollution. Fossil fuels do not last long. Okay? They'll be depleted. So we need to find an alternative energy. So this is what is the transition from fossil fuels to some other means of energy which is green in nature. Okay? So energy transition or energy transformation is a major structural change to energy supply and consumption in energy system. I got this information from the net, so you may find the same information there. But I want to use this as a means to explain. The transition to sustainable energy is another way to limit climate change. Climate change also is called as carbon capture, green energy, all these things. Okay. Another form of energy transition is renewable energy transition. Okay. The main aim is to reduce the greenhouse gas emissions, okay, from using phasing out fossil fuels and still operate on low carbon, etc. We can't say completely eliminate thermal power plants. Usually thermal power plants are the cause of gas emissions. Okay. We need to have some thermal power plants for starting up and black start capability and all those things. We can't completely eliminate. You need to have some thermal power plants, or these are called the base load plants, generate power, and then from there you try to usually slowly try to phase out and see how renewable energy can top up and supply the peak load, etc. This is a typical diagram shows energy transition. Okay, there are 8 pillars of energy transition. Discuss this later. Here the smart grids enable large-scale adoption of solar, wind and other clean energy sources. They provide real-time balancing. Okay? Because this is what the talk is about. Without smart grid, it's not possible to do this. So what is great about smart grids? How does it enable the integration of renewable energy and perform real-time balance? This is what you'll be learning at the end of this lecture. And I want you to ask me questions. Feel free to ask me question, interrupt me. You don't wait till the end. The transition from central power plants to distributed generation, like rooftop solar, microgrids, and distributed energy resources. And all these things will help in the self-healing capability of a grid, which is called as sustainability and resilience. Resilience is nothing but ability to withstand disturbances. This is nothing but the self-healing capability, which involves automatic fault detection, increase in grid stability, and reduce outages. The last term is what is called as resilience. Okay? It has what has the properties of self-healing, automated fault detection, grid stability, and outage studies. If you see this diagram, I've enlarged it for your sake. It is available in this link. Okay. It says energy transition requires many things. Industrial technological innovation, policies, grid modernization. This is what we talk about. Grid modernization and smart grids. Energy storage, decarbonization, electrification, energy efficiency, and renewable energy integration. To identify the important things, it is grid modernization, energy storage, renewable integration, and technological. These are the three important key tools which can help in energy transition. Look at this diagram. This is a very good diagram. Which are these are the factors which help in energy transition. You have renewables, okay, transmission system, bulk generation, and these are the markets. Someone said, please share screen. Are you able to see?
Yes, sir.
Yes, sir. Your screen is
Yeah,
visible.
yeah,
Clearly
the
visible.
slide number 11. Okay?
Yes, sir. It is
Yeah, yeah.
visible.
If it's not visible, please let me know.
Okay.
This is a diagram which is widely used by many people. This is used by people in electricity markets, used by researchers and control, used by researchers in what is called virtual power plants. All these things is a diagram. Okay? We are talking about mostly renewables here. How this can replace all these things. Suppose I take energy transition. Okay? I want to replace the bulk generation fossil fuel with renewables. So the percentage will be more. And these renewables should transmit power to the consumers. And these are the tools. You have energy storage, demand response, all those things. And electricity markets. Electricity markets are the means of using this renewable energy in a real-time scenario. Look at this diagram. Now we introduce a term called as sustainability. What is sustainability? You might have heard about sustainability. That means the power systems or the energy system should sustain, whether it is fossil fuel plants or renewable energy sources. It should continue throughout for the next 50, 100 years or even beyond. How do you ensure that the energy is sustainable? We know after some few years, we don't have fossil fuel. We have to depend upon solar, we have to depend upon wind, some nuclear power. How do you ensure sustainability? So energy transition, the main important property of energy transition is sustainability. You have to identify which energy sources you can use to sustain for a long duration of time till we can find new energy sources. Okay. For this, you need, suppose we are using renewable energy, we need forecasting, intelligent forecasting method. So prediction or first forecasting of renewable energy like solar or wind is very much important. This is the first task which is done in energy transition. And next is load balancing. Yeah. Load balancing means I have to balance between renewables and fossil fuels. Okay. And minimize energy waste through demand supply alignment. Okay. And finally, many people are trying to use AI driven analytics. Using electric vehicles are one such solution. Okay. So everyone must be knowing about electric vehicles. Electric vehicles are green vehicles, but we should not use fossil fuel plants to run electric vehicles. Nowadays, we are using only fossil power generation. Okay? Thermal power plants is used for charging electric vehicles. That is not green, and the purpose is not solved. So, how do you ensure that electric vehicles are charged only using green energy? Now, people talk about green hydrogen, okay? Solar, wind, etc. So, electric vehicles play a very important role. In this context, I want to inform that IIT Madras, I and my group of some faculty, we are doing a study with Kerala City Board on how electric vehicles can help in energy transition and reduce the demand supply balance. Okay, so whatever I'm telling, it's practically being done. Okay, we are attempting to use the new technologies to address the issues faced by the industry. And look at this here, this energy transition diagram. If you see here, most of them is economics everywhere. Okay? How it goes forward and backward. Energy transition, carbon emissions, reducing carbon emissions, everything, etc. Now, if you see the same diagram I've enlarged, this is completely has a societal benefit. Mostly, main aim is to reduce carbon emissions. It's also called as carbon capture. Okay, it's called carbon capture system (CCS). Nowadays, many projects are coming. We call carbon capture systems. Yeah. Yeah. And many departments, for example, IIT Madras has a department called as Energy Consortium. They address many issues for carbon capture. People from mechanical engineering, chemical engineering, electrical, okay, even we have an ocean engineering. All of us contribute to what is called as carbon capture. This all results in what is called as an energy transition. This is another diagram of the show. Okay. This is another way of diagram. We have what is a consumer, a prosumer. Okay. This is, if you look at this diagram, okay, you can see this is a renewable energy, and this is a way of energy markets of renewable energy. Marketing of renewable energy, especially wind and solar. This is nothing but, we'll discuss this later. This is something like a blockchain approach. Okay, we are doing this work with one industry. Okay. How do you do a cryptocurrency or blockchain approach of energy markets with renewable energy? Already Uttar Pradesh government has already started this. It's still on a trial basis, but it will not be very long before we can see this as a practice. Now let us talk about resilience. Talked about sustainability, resilience. What is resilience? Okay. You see here, this requires what is called as real-time grid analytics, okay, to detect instability early. That means, and preventing cascading failures. Resiliency is the ability of the system to remain in a secure and stable state, even when subjected to disturbances, either small, medium, or large. It's like an elasticity. Resilience is nothing but elasticity of a grid. Really, the grid is non-elastic. Earlier, our grid is AC systems. Now we have HVDC systems which connect all the different states. We have a HVDC, National HVDC project which connects all the states. So we have AC lines in parallel with DC lines. What does it do? It improves the stability and security of the grid. it increases the resilience. Yes, power flow can be reversed, okay, if required, okay, to ensure stability and security. This is what is called resilience. So resilience is started with the elasticity of a grid. Now, resiliency plays an important role when it comes to renewable integration. Okay. Smart grid approach provides a very good technique for resilience, but of course, it has many problems like cyber attacks. All those things are additional problems which have come with smart grids. We'll also discuss that. Next, we'll talk about decarbonization. Decarbonization also is a part of renewable energy or reducing the greenhouse gas emission. If you look at the definition, it's the process of reducing or eliminating carbon dioxide and other greenhouse gas emissions. Decarbonization is achieved primarily by shifting from fossil fuel to renewable energy, improving the efficiency by using clean fuels. The goal of decarbonization is also reaching net zero emissions. You might have heard about nowadays net zero is a term widely used by many industries. Net zero or clean energy systems. And this decarbonization involves systematic changes in power generation, industry, transport, etc. They provide a low carbon economy. Now, hydrogen energy storage is one area which is gaining more importance. Hydrogen helps in decarbonization. Now, many people, industries are producing hydrogen which can be stored and which can be used for electric traction and many other things. Even for now, we have many electric vehicles which can use hydrogen also. Hydrogen driven electric vehicles or hybrid electric vehicles. This is a typical diagram of decarbonization. It uses renewable energy integration, carbon capture. Of course, here what is important is smart grid and energy storage systems. How to improve the energy efficiency of decarbonization by using smart grid and energy storage. Then you have what is called as the green transportation. Green transportation is nothing but hydrogen transportation. Are you aware that NTPC has started a hydrogen storage? Are you aware that there's a traction? Okay, there's a, I'll not say electric traction, a hydrogen driven train, which is already in the testing phases. All these things are going to, this call comes under green transportation. Okay? All this results in decarbonization, energy transition, etc. So we want to go away from fossil fuels like diesel and then go for electric traction and green transportation. And energy sustainability. What is the link between decarbonization and energy sustainability? Energy decarbonization involves transition to clean renewable sources. Energy sustainability focuses on achieving carbon neutrality by balancing carbon emissions. If you see here, this is the diagram which shows all these things. Transition to low energy systems. Here, this is where the smart grid comes in. Digital energy management. I want to focus on the term called as digital energy. What is digital energy? Is there anything like an analog energy? Nowadays, the term industries uses digital energy. All companies like GE, Siemens, and Hitachi, they use the term called as digital energy because energy can be easily managed if it's the digital form. What is digital energy? Convert AC to DC. Is it digital energy? What is digital energy? Anyone? Because you're not asking questions, I'm asking questions. What is digital energy? Yeah, energy which you know which is divided. Is if take an AC waveform. Okay, We have an AC waveform and we try to make it a digital equivalent of an AC waveform. What is it? We take some samples. Okay? Take samples of AC waveform and try to use that sampling. It's nothing but a sampling technique. Still nothing but a sampling technique where you have more control of the energy than AC systems. AC systems are not that flexible, they're rigid. The reason we use HVDC and FACS is to make it more flexible. If you want to go beyond FACS and HVDC, you have to use what is called digital energy techniques. They have more flexibility and more control. This is where IoT and smart grid comes into picture. That's why now more industries are going into digital energy because they want to identify beyond HVDC and FACS which other techniques can make the systems more flexible, more controllable. This is where IoT and smart grid comes into picture. And of course, when you want to have grid resilience and sustainability, you should have renewables. Okay, and green hydrogen. You knew demand side management techniques like peak load reduction, load shifting, okay, value filling. All these techniques come under digital energy management and load management. Okay, and finally, what this result is, they use data-driven methods. Nowadays, with digital energy, we have a lot of data. It's called large, big data. Okay, big data is available. Okay, where we get data information from IoT devices, from PMS, etc. All this information can be used, okay, to store information and also use it for data-driven methods. This is where data-driven methods are used in modeling. Remember, I asked you a question at the beginning. Which techniques of smart grids, etc., can be used in modeling? Suppose I want to model a renewable energy system for energy sustainability. I have the data available. I have the past historical data. I have the present data, and I try to predict the future. That means I have a data. Now I want to use the data as a modeling method. There's no mathematical model involved, but I use the data as a means for gathering some information. These are called data-driven methods. Okay, that now opposite to this is mathematical modeling method. Not all problems can be mathematically defined. Those problems which cannot be written by mathematical relations, okay, they are used as data-driven methods. Finally, to achieve energy sustainability, we should have what is called as a data-driven methods. This we already seen decarbonization. Let us see renewable energy.
So what is digital twin here, sir?
Pardon me?
So in the last slide, sir, it is mentioned digital twin.
Yeah, digital twin, I'll tell you that. Good question, like that. I want all of you to ask me questions. A digital twin is nothing but a virtual representation of a physical system. Okay. Here we have what is called as a virtual representation. We have, take for example, we have a real and imaginary. Real is a physical system. An imaginary system is called the virtual system. Like in physics, we study about the virtual image, real image and virtual image. So digital twins are a category of computer networks or a modeling system, okay, which capture the physical phenomena of the existing system. For example, you have a power system. Okay, we have mathematical relations, etc. In digital twin, I try to model the system, okay, in such a way that it replicates the physical properties. Okay. I use only data. Remember, I use only data-driven methods.
So like
Yes.
so like simulation, which we are
Yes,
doing in a,
simulation we have. Simulation are mathematical models. I do simulation to get the data, isn't it?
but
I
it is
store.
all data driven, sir, because based on the physical phenomena, we put the data into uh, a system so that what kind of environment is created, and then we test it just example like engines we are testing, like then all the phenomena like the pressure and temperatures are mentioned there, and after that we simulate the things and predict the weather where up to that temperature it will fail. So kind of this is digital twin or
No, see, in digital twin, see, we have simulation models. Okay, what is the purpose of simulation models? To get some results and to get some data. Okay, so we collect all the data from simulation scenarios and store in a database. Okay, each scenario is stored in a database. Okay, now in digital twin, they use some data analytics techniques. Okay, we try to link between data, huge amounts of data. Okay, try to link the data based on the scenarios. Okay, you have a real-time simulation scenario and also data-driven scenario. Okay. Suppose a system is working in real time. Okay, I want to map it to a digital twin in such a way that I can see what is happening. Okay, the digital twin is like a prediction. Suppose I have a system which is being studied. Okay, the digital twin also shows the same, but it can go one step ahead. It can perform what is called predictive. Suppose I want to do predictive maintenance. Okay, anything I want to do predictive maintenance. This digital twins are the tools which can help provide predictive maintenance, prescriptive maintenance. These are all tools in smart grid techniques like what we call as data analytics. Okay, you correlate the data in such a way so that you can predict the futuristic behavior. Nowadays, digital twins are widely used in flexible manufacturing systems. Okay? Physical power system is one thing new which is still many people have to explore. So even industry wants to know where you can use digital twins. Okay? Even though you can't give a one short solution, one needs to explore, depend upon the situation. Okay, I'll show you some example at the end how we try to use the digital twin in some cases. It's an industry-based project. Okay. Let us see renewable integration. It's called REI. See, these are the concepts of renewable integration. Mostly, there's we have a variable distributed generation, okay. Solar and wind. Energy storage can be either mechanical, electrical, or chemical. Okay. Here, this renewable integration has created a concept called energy internet or internet of energy. Okay. We heard about IoT and internet. Okay. Now, there's a new concept called as energy internet. Okay. The same we have communication internet where we send data and information. Similarly, we have an energy internet which uses energy as a means for exchanging different types of energy between various resources. This also has the concept of energy hub. This renewable energy has what is called created many new concepts. One concept is energy internet, energy hub, virtual power plant, energy aggregator. These are the new terms which smart grid along with renewable energy has introduced new concepts. Okay, based on this, we have real-time pricing, dynamic pricing, etc. Okay, so why I have shown this in red is these are the four things: energy internet, energy hub, virtual power plants, etc., are redefining the renewable energy integration into the grid. Many new concepts are being developed. Many new formulations. Suppose I want to integrate electric vehicle to a grid. Okay, electric vehicle is nothing but a mobile energy storage. It's like a battery with mobility. It can draw power from the grid, it can sell power from the grid. Okay, it's a mobile energy storage. It has dynamics. All these things play a very important role. An electric vehicle can be charged from different locations. Even the advantages are more, there are many more disadvantages with electric vehicles also. Sometimes the grid cannot support electric vehicle if all of them are charged at the same time. So all these things require some tools and analysis. These are some of the issues with renewable integration. And some new terms with renewable integration has started is what is called the green energy corridors. Did you hear about green energy corridors? Green energy corridors are gaining more importance in India. Okay? They are transmission lines, especially created to transfer only renewable energy from one source to the another. Okay? For example, south in Tamil Nadu, we have a lot of renewable wind. So we have a green energy corridor which goes through Tamil Nadu and supplies power to the west. Okay? It's called green energy corridors. Next is wide area measurements. Here, phasor measurement units, situational awareness. The situational awareness is the new term widely used in the context of smart grid. Visualization of grid parameters. The terms like visualization, virtualization, situation awareness are the new terms which have been introduced by smart grid techniques, okay, which enables us to study the power grid more effectively. In fact, I had two of my students who have done PhD from this. They have come from industry. They know the problem better. Okay. They have come and one person has done on situational awareness for automatic metering infrastructure. It's completely new for an academician, but for an industry person, he knows the problem very well. So they try to use different tools and try to address an academic problem and find a solution. And renewable energy management, battery energy storage. These are the few initiatives of renewable energy integration. This is the green energy corridor I was telling you. Look at this diagram. The green energy corridor facilitates grid integration of large scale renewables. About 33 gigawatts capacity is envisaged. Okay. This is in Tamil Nadu. We have a green energy corridor which is going through Salem, etc. It's a 765 kV line, okay, almost developed only for renewable energy. Okay, sometimes renewable energy is unpredictable, but sometimes you have more wind power. You can't use the existing transmission lines because they are already congested. So you need a separate renewable energy corridor. It's called green energy corridor. This is one green energy corridor, and this is another in the south and the west. Okay. And here, smart grid plays an important role. How can smart grid help in renewable energy generation and energy? Here they use wide area measurements, situational awareness, so we can know how, which way the power is flowing. Okay, renewable energy can be bidirectional also. Okay, not only from one to another. So all these things, the bidirectional flows of power, this smart grid methods can monitor the flow and direction. And this is the green energy corridor. This is the Ministry of New and Renewable Energy, MNRE. If you go to the website, it talks about green energy. Almost all states they have a green, but you need green energy corridors, especially lake, only for renewable energy. And this is the typical solar parks which there. You see here, this is the Indian map. Okay. This is where more solar energy is there in the south and in the west. Last week I had been to Gujarat because they have a very good renewable offshore wind generation, lot of solar. Okay. Gujarat Electric Transmission Company called GETCO. Okay. They're the only state in our country which is using advanced techniques for renewable energy integration. They're using pump storage. They're using solar power to supply agricultural power plants during daytime. Okay. They use floating solar. Okay. So much innovation is happening in Gujarat, GETCO, Gujarat LCD Transmission Now, when it comes to renewable and wind, in Chennai, Tamil Nadu, we have what is called National Institute of Wind Energy. Anyone has been here? Did anyone come to National Institute of Wind Energy? See, this is the, and it's called NIVE, National Institute of Wind Energy. It is very close to IIT Madras campus. I go there very often. In fact, I'm one of the members which we does technical system studies. Also, there is another called National Institute of Ocean Technology next to that. Both of them are side by side. NIOT it's called. They do offshore wind generation, submarine cables, etc. Okay, both these national institutes help in renewable energy generation. You have wind. Wind is mostly on the site, on the land. Sometimes you can even have wind on the shore, offshore wind on the coast of Gujarat and Tamil Nadu. Okay, there's a lot of potential. How to use offshore wind? Once you tap the offshore wind, there's enormous potential. Renewable energy. More wind power is more availability than solar power. Solar power is only during the daytime, but wind power 24/7. Sometimes night there may be more wind power. Okay? When there is no solar, wind can act as a substitute. Okay? This is where leeway plays a very important role. This is a typical diagram how I have shown. A diagram to make you understand better how. So if we need a combination of wind and solar along with a battery energy storage. This is called a hybrid renewable energy integration. Of course, this has more of power electronic components than power systems. What you see is this is a grid isolation transformer. They're all converters, DC to DC, DC to DC, AC to DC, and all those things. This is what is called the DC thing. Okay, this is a typical diagram of a hybrid renewable energy integration. Then, if you see, go one more detail. This shows the control methods. Okay, this is one is called the power flow, shows by a thick line, and a communication flow, which is shown by a dashed line. Okay, if you see here, this is the distributed generation. This is the loads, and this is the power conversion. It's called power electronic conversion. Okay, we have different powers: solar, wind, energy storage, and flywheel. Here, flywheel energy storage is another one which is gaining more importance. It's very cheap, very easy to. So the response time is very fast. Okay, and it has low maintenance. The battery bank needs to be replaced frequently. This is a typical diagram of renewable energy generation and storage. What is important here, you can see the communication lines. See, everything is bidirectional communication. Okay, you have a local control, you have a power line. Okay, communication is bidirectional, power flow is bidirectional. This is where smart grid comes into picture. Smart grids are nothing but information and communication technologies, ICT, where communication and power can flow in both directions. That means you can see what is happening on the other side of the tunnel. This is another diagram which shows automatic renewable energy integration, a typical diagram. Okay, so some of the calculations our students have used. Okay. The typical values. Okay, get power from different sources. How you connect it to the grid is a point of common coupling, and you have what is called automatic switch box. This is an electrolyzer, something like this is a battery energy storage, and this is a launch server. All these things are methods. They have programmable logic controllers. All this is how a typical setup of renewable energy integration of different capacities. If you see here, some of them are in small kilowatts, 5 kilowatts, 1 kilowatt, 4 kilowatt. Okay, fuel cell has 1200 watts, 1 kilowatt. These are all small. You need to aggregate all of them. Suppose you aggregate them, they come to about some megawatt levels. So energy aggregation is a very important thing which comes with renewable energy and smart grids. This is a typical energy management system in renewable energy. Suppose I have wind and solar, which is coming to a grid. The blue one is the power flow. Here, this is energy management system. The blue one is the power flow. And here, this is the power bus connected to the grid. Okay. And this is what is happening inside an energy management system. I call it as renewable energy management system. Collect the data, it's called data logging. Then we have the forecasting model of the renewable energy. We already know the load. Okay? And we try to map the generation to the load. And then we see the dispatching strategies. We try to see which energy management strategy is important. Then we'll give a control signal to the energy storage. Here we do system security and economic analysis. When I talk about system security, okay, there are many more studies. Security assessment, contingency analysis, N-1 contingency, many more studies. Okay. Now, this is for a renewable energy alone. Now, suppose I integrate energy transition and energy sustainability. How will the diagram change? What systems, what will change under this? Suppose I want to integrate, okay, energy sustainability and grid resilience. That is the main topic. What will change in this? Same thing, renewable energy is there. Inputs are the same. Input is the same, output is the same. Only what is happening in the energy management system keeps changing. What will change? Can anyone tell? Input is the same. We have wind farm, renewable energy is there, output is the same. Of course, you have energy store, everything is same. What will change? The dispatch strategies, okay, and many more modules will come here. What are those modules? Stability, security, many more things will come. This is where more innovation is required. This is what industry is looking for. Because industry wants to take up this project, it needs ideas. This is where ideas are generated. You need more such system studies, more blocks like this. What will be the new blocks in this? This is still an open question and open challenge. No one knows. Because no one has explored what is called energy sustainability. Grid resilience, of course, we'll call grid resilience nothing but restoration, power system restoration. So, some restoration strategies will come here, some control strategies will come here. This control to energy system studies. We have many more blocks coming in this, which are related to resilience and sustainability. Energy storage, of course, you already have energy storage. What else do you need for grid resilience? This is where the challenge is. No one knows the answer. Industries don't know, they only add something. You need SCADA. Okay. Some people they add some terms. How can SCADA help in grid resilience, automation, control, etc.? We'll see as we proceed. Same thing. If you see here, the same diagram I've shown, you need a forecasting model and you need much more beyond economic analysis systems. In fact, one of my PhD students, she's doing a work in this related. Let me share that idea because I have to share ideas with a lot of faculty. Building what is called cyber physical system. Did you hear about the term cyber physical systems? Cyber physical systems are the solution to this. Why? Cyber is nothing but computing. If you look at the word cyber, it's nothing but the thinking brain. Cyber consists of communication, control. Okay? Cyber control, communication and control. Two things. It's complete communication, control, and computation. This is what is called cyber. Cyber physical systems is the interface between a physical system and a cyber system. Physical system is a power plant, the wind engine. What is the cyber system? It contains computation, control, and communication. These three interlinked and properly executed can help in grid resilience and sustainability. I would like to say here, no one has explored this. How to use cyber physical systems for energy sustainability. This is the topic my PhD student is working. They're using graph theory and complex networks, okay, to find a solution. So this is nothing but a research problem. And now it comes to smart grids. Okay, smart grid is nothing but a collection of data. Okay, data collected, database. Of course, battery energy management system. This is a smart grid. Suppose you want to use renewable energy. Okay, you have an optimization. You have everything is data. You collect the data. That's why it's called data-driven methods. Remember, the future of energy systems is data-driven. Okay, even though you do the simulation, you store it in data. This data contains lot of knowledge. It contains some information. How to extract knowledge from this data? This is what nowadays many people are trying to use machine learning and AI methods. I have a lot of data. I want to extract. It's like finding needle in a haystack. The haystack is nothing but the data. How do you find the needle inside this? One or two needles. This requires data analytics. This is where nowadays everywhere you find data analytics. Many people want to use data analytics. They do not know how to use. They only know the programming language, SQL. You talk about them, they'll say SQL. Okay. What does it do? It's a structured query language. It's nothing but asking questions like ChatGPT. Many people know all about the coding, but coding is something different. How do you find the knowledge in a data? Because you're collecting the data and heaping all the data together. It's like a data warehouse. It's called data mining techniques. Okay? This is where they use AI and machine learning to identify the knowledge in the data. And wind energy, as I said, is gaining more importance. Yeah. This is a diagram which I've taken from the net long time back. You collect all the wind farms. Okay, optical fiber is used to collect all data and use it for a wind farm. So SCADA for wind plays a very important. Remember, I keep telling, okay, the wind is the future for energy sustainability, not the solar. Solar is already there. Solar is available only during the daytime. But wind has more potential we have not tapped because it's unpredictable. It's not deterministic. See, wind energy is always probabilistic, it is random, okay, stochastic. Whereas solar, it's a definite half sine wave during the daytime. Wind can change direction, it can change speed, velocity, many things will change. But how to tap wind energy is still the question. Okay? If we can tap wind energy and convert that probabilistic to deterministic, okay, that will solve a problem. In this context, I want to tell that IIT Madras, I and another faculty are working with DTU in Denmark. We got a project from DST and Denmark government. How to use wind energy for electricity market. It will show at the end. Yes. This is the wind farm SCADA. If you see in many places, especially Gujarat, Tamil Nadu, and AP, you have a wind farm SCADA. They collect all the information. Okay, this is not the power generation. Okay, only they collect the data, how much wind each wind farm. Okay, this is called the wind farm. Okay, how much power it is generating. Okay, this power can change. Sometimes some of the wind will, wind turbines stop rotating. Okay, due to some reason. Even though they're supposed to generate, suppose I have 5 megawatt for one wind farm, there are 4 wind farms, so 20 megawatt is expected. But I will not get 20. Sometimes I get 10. Okay. So by using this SCADA, I can tell how much power I'm likely to get. Okay. I can predict how much wind power is expected the next 24 hours, next week, etc. That's why you need wind farm SCADA for wind generation forecasting. Let's talk about energy sustainability. Here I talk about digital energy, grid resilience. Okay. What is grid resilience? Already I mentioned, now I'll go once again. Grid resilience in power nets is an important area nowadays. It indicates the ability of the network to withstand large disturbances and yet remain operational to supply power. Grid resilience is a complex optimization process involving control and automation. Here we go into control and automation. The futuristic power grids encompasses all properties of resilience, sustainability, and restorative and autonomous operation. Look at this term. I want to use now. I use it to come as autonomous operation. Nowadays, futuristic grids are completely autonomous, called self-healing, resilient. That means, okay, in case of a fault, okay, or any disturbance, the system can recover on its own. It can repair on its own. That is called resiliency or elasticity. And it can sustain for long durations through battery energy storage and restore it. In case of any disturbance, it should come back to the normal state or near normal state. So that power is supplied to the consumer. This is what is called resilience. And many industries want to have a solution. Can renewable energy enhance the resilience? Can renewable energy help in sustainability? Sometimes yes, sometimes no. You need to have energy storage option as well. If you have all of them, then you can have an autonomous operation. The grid can sustain even in case of disturbances. If you remember, last year, 2024 or early 2025, there was a strong snow, there was a snowstorm in the US. Okay? All the power lines have collapsed. There's no power. Okay? They have renewable energy. Even same thing happened in Australia, UK. They're using a lot of renewable energy. They don't have any, they shut down all the thermal power plants. There's a lot of storm. Okay? The snowstorm had come. All the lines, snow had accumulated on the transmission lines. The weight was heavy and the transmission lines broke. The one was in Texas, I think, I'm not sure. And suddenly they have to revive the thermal power plants. They have not planned for this. So planning is a very important thing for energy sustainability. Renewable energy alone is not a solution. It supplements and complements, but it cannot replace thermal power plant. That's why I said thermal power plant should be there as a black start operation to start a unit. Okay, keep it operational. Then you top up with other renewable generation, but never shut down the thermal power plants. Of course, nuclear power plants are essential. If you've seen, our Prime Minister Modi was telling, we should have nuclear power plants. He was talking about renewable energy generation 2030. Okay? Now, last year he was saying we need to have nuclear power plants. See the sudden transition, okay, from renewable to nuclear. Because we know nuclear renewable energy, we are unable to tap. Okay. Domestic. If you have a nuclear energy, you need to supply all the loads. Then you can have sustainability and resilience. So this is the diagram I have shown. Okay, energy sustainability versus resilience. You can see this is the power flow, this is information flow. This is a typical schematic diagram. This is where a smart grid approach to energy transition and resilience. I took this from from the net. You can see here power flow from generation, transmission to distribution substation. Here they use wide area network, neighborhood area network, and home area. And different service providers. This is where the IT companies come into picture. Okay. Different renewable integration. Okay. This is what is called the energy storage. Everything is bidirectional. This is what is called energy transition. I want to reduce this fossil fuel. I make it minimum. It should still be operational, but we should slowly, gradually change from fossil fired to renewable. And these are some of the system studies. Okay, remember I was asking, okay, typical diagram, how do you enhance the grid resilience? I have resilience. I want to enhance it further. You know what is enhancement? I was trying to improve. Okay. Sustainability of resilience is one. How to enhance grid resilience? Okay. Grid resilience enhancement is like a closed loop, physical or operational capability. Look at these states: prevention, degradation, restoration, adaptation. This is called the grid resiliency assessment. This is the most important thing. Okay. One is in green, one is in blue. Can you tell me what is green and what is blue? Why they use different colors? What does green indicate? What does blue indicate? This is grid resilience assessment. This is an enhanced. Look at this state: prevention state, degradation state, restoration state, adaptation state. Means the grid can be under these four states. First, prevention is better than cure. Next, degrade. The system degrades. Before it collapses, I should do some restoration strategies. Then I should adapt to the environment. This is what is called grid resilience. I have one MS student working in this area, grid resilience. Okay. The different operating states: prevention state, degradation state, restoration state, and adaptation state. Okay. For this, you need grid information, weather information. When is a cyclone likely to occur? Okay. And then I need hazard modeling and grid resilience index. What is grid resilience index? How do you define grid resilience? It's a key performance indicator called KPI. How do you define grid resilience? Can anyone tell? These are the new terms. These are the research points or research topics which grow out of this grid resilience. They're not textbooks as such. Only we collect from available sources of information. We teach students, we tell research students to work in this area. We make them think. Okay, they come with their own resilience index, which should lie between 0 and 1. Okay. Of course, 1 is highly resilient, 0 is very not resilient. So, how do you define a grid resilience? Is it a stability? Is it a security? Or is it a fault? So, grid resilience index is a combination of all studies. So, security study, stability study, and fault study. It's a combination of all three studies. So, how do you formulate such a problem? So,
So can it be said as how fast or how rapidly the grid recover?
Yeah, grid should recover exactly. It's not only recover, it should sustain. Is it stability? In case what stability? Is it a steady state, dynamic, or transient? If it is system stability, if it is security, is it steady state security or dynamic security or transient security? Okay. Many possibilities are there. You need a combination of all these things. You need, okay, for example, you need to collect each and every modeling technique and involve in the grid resilience. Next, energy sustainability. This is what is called energy. Now we'll come to energy storage. See, energy storage enhances the resilience. Okay, energy storage system ESS. Okay, it enhances the resilience. How it provides the support, energy support, backup support. Okay, in case the grid fails, there's a energy storage to support the power. Okay, you are increasing the reliability and resilience of the grid. Okay, this makes grid flexible and reliable. And we are trying to use some technologies like digital twin, blockchain, AI, ML. Because some of our students are trying to use, still they have not come across, but they still have to do some more work. How to make this smart grid technology work on this. Decarbonization we have seen. Next, energy hub. Okay. Now, energy hub is a new concept widely used. Look at this diagram. This is a very good diagram. Okay. Concept of energy hub is something new. Look at this. You have electrical energy, chemical energy, thermal energy, different types of energy. Okay. Joined together to give me electricity, heating, and cooling. Understand? See, the inputs are different, the outputs are different. This is the concept of an energy hub. This is widely used and implemented in UK. Understand? This was, this idea was, I'm not say developed, it took place in a research group in UK. Okay. Look at this idea. Okay. I have different inputs, energies, so different types of energy, and I use it for heating and cooling. Let's into electricity, heating, and nowadays this is widely used. This concept is used in our, what you call as gated households. Many apartments, gated households, they use electricity, heating, and cooling. Okay. They use rooftop solar and electricity. Okay. They use solar PV, they use thermal solar and electricity. How they integrate between all of them. So this is the concept of energy hub. Where it can be used, how it can be used. This is how smart grid is. Yeah, this is the concept of energy hub. Look at this diagram. Same thing I've shown it by here. We have wind, solar, buildings. These are supplying to the grid. This is an electric grid. The blue one is an electrical network. Okay. This is a chemical network, gas network. This is the thermal network. Thermal is heat, gas is this, is an electrical. So wind and solar power supply to the electrical network, and CA is compressed air energy storage. This is bidirectional. Okay. They can supply power to the electrical grid as well as they can supply here. Battery is also bidirectional. This is unidirectional. Okay. And the electrical grid can be used for heating. It's called combined heat and power, CH. Okay. They use electrolysis and LCD product. This is called small storage, hydrogen energy. This is where hydrogen energy storage is gaining more importance. Okay. This is where biofuels. These are electric vehicles. Remember, electric vehicles play a very important role. Here, we introduced a new thing called as the transportation network. We have electric network, fuel network, gas network. And output is a transportation network. Even though this was not anticipated, nowadays transportation network is entirely new. Now, how do you solve this problem? We have a student in mechanical engineering who is doing this. Okay, he's trying to integrate all of them. Okay, each of them is renewable. Thermal gasification. This biogas is nothing but municipal solid waste, MSW. Everything is renewable. Okay, how do you solve this problem? It's very easy to show by means of a diagram. How do you model this? This is what is called energy storage systems. Please think about it and let me know. There's more than other network. Electric transportation network is one such thing. Many things can come out of it. Look at this underground storage, hydrogen storage. Everything is a storage. Battery energy storage. You can't depend on battery energy storage. You need large storage, hydrogen energy storage. He said a small scale hydrogen. Can I be a large scale? Pumped storage. Okay. In addition to this, I can even have a water network. Water network pumped storage can also come here. I have electricity, thermal and gas. I can even have a water network, which is nothing but pumped storage. All this can come into picture. Okay, that's why this is what is called energy storage system. This will help with the grid resilience and sustainability. In case there's no electric network, I can use thermal network. Okay. In case there is no gas network, can supply for all of it. There's a complete integration of all. This is what is the concept of energy hub. Understand? And one important thing is called energy storage system. This is called zinc bromide battery. This is called red flow. It's called red oxide flow batteries. It's called red flow batteries. It's called red oxide flow batteries. They can store large amounts of wind energy. Because wind energy, sometimes it can be in the form of megawatts. Okay, where do you store large amounts of wind? Okay, of course, the moment you get wind, you can transmit. Suppose there's no demand in the night. Only demand is there in the daytime. So you need to store. How much can you store? Okay. This redox flow batteries can store up to gigawatts of energy. And there's only one company in the world, two companies. One is there in Japan called Sumitomo Electric. They're making 50 megawatts of energy storage. Remember, 50 megawatts of energy storage. And they're increasing. Okay, they're converting the R&D into a product. There's so much of demand. For example, in India, we have Ladakh. What about Ladakh? It has so much of wind and solar. We need energy storage there. How do you do energy storage? It's in the order of megawatts. Battery storage cannot be used. It's very expensive. Not only expensive, you need to depend on some other supplier, some other country. So redox flow batteries are the future of energy storage, the order of megawatts. 50 megawatts, can even go up to 100 megawatts. Okay. They have what is called the deep discharge. Okay. And hydrogen as a vehicle fuel. Okay. Hydrogen storage can also be used. Fuel cell. This is a typical hydrogen energy storage. Okay. Variable speed wind turbine. Remember, wind turbine output is used for energy storage using fuel cell. Now, there's one thing called as a virtual inertia. Did you hear about this term, virtual inertia?
Yes, sir.
Yeah, many people are doing PhD in this. Many people are doing. I've seen virtual synchronous machines. The term virtual inertia is gaining complete importance. The research topics, variable frequency drives, everything comes from. See, modern power system, they have synchronous based system to inverter dominated system. Now, nowadays, everybody is going from inverter dominated system, synchronous machine to inverter dominated system. Okay. Now, this is what is called a flywheel energy storage. They're going to completely change the landscape of energy power and systems, integration with renewable. This is what is called flywheels. Remember, I talked about energy storage. Flywheel energy storage is one of the most important things. Okay, you have a flywheel, you have a wind energy. Okay, I have a diesel generator, DG, a wind energy. I have a load reactive power compensator. I have a flywheel energy storage. It is bidirectional. Okay, even though there's no battery energy storage here. Wind energy is there. I have a DG. I have a load. This is reactive power compensator. This flywheel energy storage serves as a battery energy storage. Okay? So they are going to find an alternative to battery energy storage. So you don't need batteries, lithium-ion batteries. Many people are very expensive. You have to import them. Okay. Nowadays, many people want to go into the area of flywheel energy storage. These are the solutions for energy storage of the future. This is a typical time. Flywheel energy storage. Okay. This usually comes under microgrid energy management. And they're fast responding. The most important thing, they're very fast responding. And they use magnetic bearings. Nowadays, they use magnetic bearings. You know what is magnetic bearings? There's no friction. There's no ball bearings. Okay? It's called magnetic bearing. They'll float. So response time is faster. This will help in the grid resilience. So flywheel energy storage, it helps in grid stability. It's bidirectional. This is charge and discharge. It is also called as inverters with virtual inertia. Okay, many researchers are pointing towards using inverters with virtual inertia control algorithms. How can they help in stabilizing? Mostly in microgrids. For example, microgrids, standalone microgrids. They don't get supply from the grid. Okay? But still, in case of a demand, you can store wind energy or solar energy in a system. You have many such flywheel energy storage systems. This is elasticity. This enhances the grid elasticity because it's a dynamic storage. That's why you can even have the diesel generator, as I said, but this is enough to absorb all the shocks. Any disturbances it can absorb. It's like a battery energy storage because it is rotating energy storage. It can absorb any disturbances. Now, smart grids. Now we talked about resiliency and other things. Let us see how smart grids can help the solution. Any questions you will have? I'll share the slides, don't worry. But I want you to see how can smart grid find a solution. This is how the typical smart grids are taken. Electromechanical era, digital era, and convergence era. This digital, I can replay this era with energy. Electromechanical energy, digital energy, and convergence. Now remember, I talked about digital energy. The same thing. electromechanical, synchronous generators. What is digital energy? And you need a converter. This idea started from 1960s. This is how the smart grid had progressed. This is the customer expectations. Remember, it's not the technical growth. The customer expects the digital energy is going to solve their problems. This is how smart grids will help solve that problem. This is the digital energy. You can see here. When I say about digital energy, see the diagram. Everything is this is digital protection and control, digital fault analysis, self-healing grid, communications, substation monitoring. Everything is digital in nature in the future. Okay? You have a power plant. Everything is going to be digital, automated meter reading, AMR. This process of monitoring the system through digital techniques is also called as digital analysis. Digital fault analysis. See, this is the one which is gaining more digital fault analysis and self-healing grids. Okay. What is digital fault analysis? This is a term used by industry. Okay. What is digital fault analysis? But I gave a
Use-
list of questions. Yes,
Using
please tell.
using fault samples and making an analysis.
See, for example, okay, that you almost close. See, we use methods like PMUs. Okay, what does PMU do? It take samples, several samples per second. Okay, so we use the sampling method. Okay, to detect the location of the fault. Suppose I'm using PMUs, I can detect which machine is going out of synchronism. Can even detect the fault on the transmission lines. PMUs are widely used for monitoring, protection, and control. This is what is called digital fault analysis. They never use the term PMU. Understand? They use that we know synchronous phasor measurements, okay? Phasor measurement units. They use digital sampling techniques, signal processing, digital signal processing, etc. Instead of using the term, many industries use the term digital fault analysis. Same thing with digital protection and control. They use digital control techniques, distributed control techniques. Okay, so this is where the new concepts application for protection and control are digital protection, digital fault analysis, and some more terms may also come in the future like digital energy trading. I do not know, many things may come. Okay? It depends upon which new techniques you are using. So smart grid helps us in identifying methods, okay, which can be used for system studies, mostly for to help in enhancing the resilience and sustainability. This is the typical diagram which shows smart grids of we have energy storage, electric vehicles, smart city, and here renewables, okay, pump storage. It's a hydro means pump storage, solar power. See, all this is power generation, this is power transmission, this is distribution. Everything is bi-direction. Okay. Now we want to reduce the thermal, not remove it, and enhance the other things. And this is some of the techniques. Look at this. It's a future electricity system. Future electric system. Of future electricity system. There are many things which are used. Okay. The red ones are which are important. Distributed energy storage, distributed generation, electric vehicles, advanced metering infrastructure, and demand side management. These are the one which influence the futuristic grid. They use communication, data analytics, everything, etc. And smart power grids. Okay. It uses all types of information. Okay. Electric vehicles, battery energy storage, okay, hydro plant, thermal, different types of, we have to reduce the thermal, use more of renewables and hydropower. And this is what's called energy balance. This is the more, I should have shown this slide first, but this is what it is. Look at this diagram. You can call it a load frequency control. This is the generation, this is the demand. We have renewable here, we have different consumers, electric vehicles, energy management system, energy storage, etc. Generation, transmission, and distribution with renewable energy in grids. Just to show how generation, distribution. Okay. If you see here, the users are more. Generation is less, distribution is of course there. Look at the users. There are more number of users for renewable energy. And this is smart grid is nothing but the interconnection of blocks. Finally, if you see here, smart grid is nothing but the interconnection of blocks. This is the grids. This is a typical grid, how they are connecting each one. Many new blocks can come. Storage is one, renewable energy integration, okay. Smart buildings, cyber security, of course, this is gaining. Look at this term called as digital substation. It's a new term. What is called a digital substation? I talked about digital energy. Digital substation is something new. Substation which is completely unmanned substations are digital substations. Unmanned substations are called digital substations. Now, I'll spend last few minutes. This is the work we did for Accenture. We did a work on digital twins for autonomous self-healing power networks for grid automation and sustainability. We just finished in 2025. We developed a small digital twin for self-healing grids for sustainability and resilience. This is how we did. We have a physical layer, a communication layer, presentation layer, all those things. And this is how we did. We an actual power system. We use raw data, Python API, use operator control. Okay. This is what the diagram architecture we used. Use all this is where smart grid comes. All okay. PSCAD simulation, communication layer, presentation layer, resilience evaluation. Okay. This is how we realized this. Okay. We took a small 9-bus system, tried to validate how this can work. Okay. This we simulated in PSCAD. Simulated this in PS to generate the data. We generated the data, collected all the data, and this we used some data analytics, etc. This is how we used a Python script. Okay. Python API for PSCAD automation. The new PSCAD has a Python compatible. Okay. This we have used. So whatever I am preaching, we have already practiced and practicing also. And this is another we did for Shell. Okay. This is also grid resilience, automated grid management, data analytics, interoperability, and all these things for grid automation. It's called SOGNO, service-based open source grid automation. This is how it is. Remember, I asked you which studies do you do for grid resilience? You need network topology processor, you need state estimation, network reconfiguration, security assessment, online load flow, OPF, volt var control, capacitor switching, transformer tap changing, voltage regulator, restriction. All these things are required for grid resilience. We did this for an industry. That's it. So whatever I'm showing, this is how we have done. Each and every module we have developed. Okay? We are still doing it now. It's confidential, but I'm sharing. And this is what it is. Remember, this is grid resilience. This is the project we are doing with Denmark, where we use hydrogen storage. Okay? Offshore wind. You generate the power, hydrogen, you store it, and sell it in the electricity market. You use blockchain trading. Finance. This is how it works. This is the project we got from DST recently. We are still working on that. So please keep this confidential. We just want to show what is the scope for energy markets. Mostly wind. Wind and hydrogen storage can be used in electricity markets and blockchain. This is how we are doing. Okay. Source planning, operational planning, plan design. We use day ahead markets. This is how, suppose you have wind. How do you use wind energy for that? Wind plus hydrogen production, solar plus hydrogen production, all this. So this will help in the resiliency of the grid. Understand? No, I'll stop here. Any questions? Exactly by 10.
Thank you so much, sir, for such an insightful session and briefing us about the cyber physical system, the importance of data analytics, and how to integrate the AI and ML for trapping the wind energy data. So it's really an insightful session. Thank you so much, sir. Now we'll move ahead with the question and answer session. So participants, please come up with your question. Thank you.
Okay. Thank you all. This is a lot of research topics because you're all of you are teachers. Should ignite you to think. Okay? Give this, discuss with your students. You can also do it independently. You can take up these topics as a research. You can publish. Many conferences are there. This time, NPSC is being held in IIT Patna. Okay, so there are a lot of topics related to this. Okay, so good. All the best. Thank you very much.
Sir, one question is the modernization will uh, reduce the theft of electricity. How the digital and all these issues it will help.
Can you repeat it once again, please?
All this can will reduce the electricity theft. Actually, some
No.
people they are they do for fraud and they cheat,
Yes,
and
yes.
theft can be prevented
Yes,
with the help
certainly,
of
sir.
digital meter.
Yeah. Now we have smart meters. Digital meters are different. Smart meters are different. Okay. Digital meters can only measure and tell you what it is. Smart meters can help you detect where the theft has occurred, at which location. Okay. There are many more things. See, there one thing is technical losses and not technical losses. This theft is mostly to non-technical losses. Okay, because you have a wired information as a wireless information. Okay, no one can stop a wireless data. For some theft is there. You can receive it over your Wi-Fi. Okay, you can easily locate that person. Earlier we used to depend upon the wired information. Now they cut the wire. Okay, but still you can get the information through wireless. This is where IoT plays an important role. This is what is called situational awareness. This is what is called last mile connectivity. Many villages they are using this technique. For example, in South, Adani has completely installed all the smart meters. Okay, everyone is expected to pay. You know, everyone is expected to pay the power. There may be free power, but still accountability will be there. So there will be no power theft with smart meters. Okay. Hope this answers
Okay,
your
thank you,
question.
sir. Thank you.
Thank you very much. Thank you, Baba.
Any further questions? Participants, please be quick.
Sir. Hello. Am I audible, sir?
Yes, sir, you're audible.
I think Sir has left.
Sir has left.
Oh, I see.
So that is the reason I also stopped asking question.
All right. Okay. All right. No issue. Just contact him.
Yes,
Whether
sir.
you wish to join once again. Not for this question. I mean, you are supposed to take a photograph.
Yes, sir, I'll talk with sir and
Yeah.
yes, sir. Yes, sir. Participants, just wait for a moment.
मैम मेरी रिक्वेस्ट है, हमें खाना भी खाना है मैम, प्लीज वो फीडबैक लिंक शेयर कर दीजिए, इतना हम भर लेंगे उसको.
Yes, sir, just few seconds. Sure, we'll share. I think link has been shared. Please check.
From the organizer side, we provide the email of the resource person of session 10. So if you have any doubts, so you may contact with the resource person over mail also.
Hello. Hello.
Yes,
You are audible. Tell me.
Sir,
I
link is
sir has
not
joined.
link is not in link is not opening. Session 10. Hello.
Sir, this link is opening. Yeah, you will open it from your registered ID. So Sir is there. So Bhivan, Dr. Shaha. Dr. Shaha.
Yes, I'm here.
Sir is rejoined. So if you have any questions or queries, you may proceed.
Okay. Thank you. Thank you. Sir, I really enjoyed your lecture. So many things has been explored here. One very basic thing I would like to hear from you.
yes.
You said resiliency and then the automatic restoration.
Yes.
Right. Automatic restorations, we may think of it is quite similar to self-healing. Now here,
Yes.
without control, how much, I mean, the power system engineers or power system researchers, we will be able to do research on this for getting this self-healing or this enhancing the resiliency. Because the control means, again, we have to collaborate or If it is really needed, then definitely we have to collaborate. Without collaborations, how much we can do? If you just give
Yeah,
some
that's
light
a
on
very
that.
good
Thank you.
question. I'll tell you. See, you don't need control collaboration. See, electrical engineers, no, we study control, load frequency control, automatic generation control. You know what are the controls in power systems we study? We study about load frequency, automatic generation control, volt to hour control, real power control, reactive power control. We study on their own. Okay? When it comes to restoration or resiliency, okay, you should know at which state the network is. Okay, is it in a secure state or insecure state? If it is an insecure state, is it in emergency state? Is it in a restorative? Many operating states are there. Okay, to identify the operating states of a power system, you need to have what is called system identification methods. Okay, okay, you need to identify where the operating state of the power system is. Okay, based on the operating state of the power system, then you have to implement the control actions, either preventive control or corrective control. Here, preventive control, we try to change, okay, the generation, increase the generation, decrease the generation, okay, and change the what is that called, tap changing, you know, transformer tap changing to adjust the voltage. When you have to adjust the voltage, adjust the power. Power through increase or decrease in the generation or load. First, you do preventive. If preventive fails, then you have to do corrective. Corrective where you shut down the load or increase the generation, add new generation. Okay, switch on transmission lines. Suppose you add new transmission lines. Okay, that is corrective control. Because one line is overloaded. Okay, before the line trips, you have to switch on another transmission line in parallel. Okay, if there is an existing line, that will improve the stability. Listen, all these things require real-time control. Okay, switching on transmission lines in parallel, switching on a generator, okay, or shutting down a load. These are all corrective control actions.
That should be occurring in real time. So that means suppose rerouting of power. So when one line will be out, rerouting of power that should also be carried out on real time.
Yeah, rerouting power can be done provided there is a parallel path. Provided the line is not congested.
No,
good.
sir,
What you
in
said
an
is right.
interconnected power system, even if there is no parallel path.
Interconnected power system, it depends upon if it's a okay, meshed network. Okay, if it's a mesh network, there'll be alternative paths available. Usually, most of the networks are interconnected where there'll be wheeling of power. You know, power wheeling, okay, where power is circulated from one area to another to transmission lines. Okay, there'll always be a network.
The whole thing, I mean, say outage of this, identification of the outage, and then calculation of all the possibilities that, yes, there are so many interconnection. So which way, if I transfer the additional amount, it will not be, overloaded. So all the calculations should be carried out in real time. I mean,
Yeah, these things are called security assessment studies, security assessment and contingency analysis. Okay. They use N-1 contingency. We use line outage distribution factor, okay, generation outage factors. All these things are done in security assessment. So there they come to know which line is likely to get overloaded, okay, in case there is an outage. We try to see how much the line overloading occurs. Okay. So with this, we know what preventive actions we can take or what corrective actions we can take. All this is done in real time. Nowadays, security analysis is always done in real time because we get all the values from real time measurements are there. They do real-time state estimation. Okay, power flows are done in real time. Okay. All the plan, this is contingency analysis, and they're done are a part of power system planning studies. Okay.
Yeah, that is
System goes into
important.
operation, everything is done in a real time environment.
Okay, sir. Okay, thank you very
This
much.
will help in the resilience, as you said, no, restoration.
Good job. Good evening, sir. I have just one question regarding digital twin that you have mentioned.
Yes, please.
So can you suggest some softwares where it is exactly possible to replicate? For example, I work in the area of condition monitoring of high voltage systems. So here it is extremely difficult to get the data from the high voltage system directly from a power utility. So in the context of condition monitoring, this digital twin and application of AI and machine learning is now becoming a very emerging area of research.
Exactly.
So I have just one question, sir. That can you suggest that which software is better for modeling? Is it ANSYS or COMSOL or something like that?
See,
suggest for us students like.
Yeah, COMSOL is widely used nowadays. Okay, but how to use COMSOL, no one knows for distinct.
Okay, sir.
See, nowadays, see, we always tell our students to do from scratch. Okay. Okay. See, you can use a software for generating the data. Okay. For example, you know about ETAP. ETAP software is coming up with a digital twin. It's quite expensive. It is not available in our country also.
But is it possible to model some fault inside the insulation system using ETAP?
Yeah, ETAP, I do not know whether you can use PSCAD for that.
Okay.
PSCAD can be used in detail. I do not know if ETAP can be used for simulating faults. Only external faults you can create. I do not know about internal faults.
Okay, thank you very much, sir.
Yeah, I'm sure PSCAD is capable of doing internal faults, to my knowledge. Okay, interwinding faults, because PSCAD has an internal representation of the windings. You can even create a fault, interwinding fault, like that in PSCAD, and generate the data. Finally, what you need a collection of data. Okay?
Yes.
Which software you use is up to you. Okay? For example, some of the students prefer to use their own software. That means they write the program either in MATLAB or PSCAD or to generate the data, because they have control over the modeling. Okay, one should not depend upon any software to generate the data. Okay?
Thank you, sir.
Any further questions? I think
No, ma'am. No questions.
Okay, so now we will close the question and answer session, and I'll request participants and everyone to please switch on your camera. I'll request everyone to please switch on the camera.
Thank you. Thank you all.
Thank you once again, sir, for giving your valuable time. Thank you.
Thank you, everyone. If you have any questions, please mail it to the coordinator. They'll send me the questions and then reply to you.
Yes, sir. Yes, sir.
Thank you, sir. It was very informative.
Very nice to have so an interactive session. Okay? So many questions. The more the questions, the better it is. Understand? Okay? Please don't hesitate to write to the coordinators. They'll send me the questions and give me some time. I'll reply detail how to proceed and all those things.
Your PowerPoint was very nice.
Thank you.
They were very elaborative, and the font was also
Sure.
bigger, so it was easy to see, and diagrams were also clear.
Thank you very much, sir.
Thank you very much, sir.
Thank you, thank you.
Thank you, sir. Thanks a lot.
So we can leave now.
Okay, good night.
Yes, sir.
Yes,
Yes,
sir.
sir.
Good night, sir.
Good night, good night.